we have 3 more sessions. So it's our 4th session and we have 3 more sessions. And as I said, those 3 sessions will be in January, and we will look at doing these things we are doing now in the cloud. Okay, so the book that I'm giving you, these tutorials or exercises, has lots and lots of examples. So it's I forget if I have uploaded the book itself, but so I have selected those things that I felt are common use cases. And so today we are going to look at anomaly detection. Because it's a little different than just normal classification. We will see why. And so what I've omitted is text classification, but I put the task on the VLE, right? So those of you who are interested, and that's going to be useful for the assignment, which I'm going to talk to you about at the end of today's class. And that's the final assignment. So next, the January sessions, we will, it's about imparting a skill, and so there won't be any more assignments, because I don't want everybody will start giving me assignments right at that point. So I want you not to have any assignments after this. So I realized that I had probably not exposed this recommendation system submission link. I have exposed the task, but I haven't exposed the link. So, so that's the first task, right, that you need to do this week. But the assignment, I will set a deadline in first week of January. Yes, Niroshananda.
Sir, for the task 2, we couldn't find the data sets in that video classes. In the website, we couldn't find that the data sets. I searched for the data set, but I couldn't find it.
Wait a minute, let me see. The recommendation. Is it for the recommendation?
Yes, sir. Yes, sir.
Right. Okay, thank you for informing me. I'll upload that.
Thank you, sir.
Okay. And also, I think I hadn't exposed the submission link, right? So even if you did it, that would have been a problem. So you should do it this week before you go on a small break for Christmas. I mean, these tasks are basically, obviously you're not doing something from scratch, right? You're just trying to follow the tutorial and then just do it. I hope you have had a go at the assignment, which is that was like a fairly simple assignment, right? The final assignment is a little more open-ended. That means it the data set is still given, but you have to. There's a lot of scope for you to do your own thing. That's the whole idea. Okay, so so in January, I will not give any more assignments, but of course we will do tasks like this that help you to kind of have a practice of what's to be done, right? So last time we looked at clustering because it's a bit of a area that is not so crisp and nice as classification, right? And where you need to make a lot of decisions. So that's why I chose that particular task. At this time, we are going to look at anomaly detection, which we will see is different from classifying anomalies. Well, you may be able to classify anomalies, but why it may be difficult. And then I've also in the VLE put the task 5 for text classification. That is more or less useful for the assignment. So you don't have to do task 5, but you can read it, and that will give you some ideas on how to do task 5, the assignment. So I'm going to really not put submission links for clustering, anomaly detection, or text classification, right? So those 3 I am giving the tasks, but it's up to you. But task 2, which was recommendation systems, I put a submission link for this week, right? Right. I mean, if there are questions about that, let's talk about it after the session. Right. I'm going to knock off my video. Right. Anomaly detection. So what is it? And what are its aspects? What are the typical applications? What are the types of anomaly detection? Actually, I'm not going to do the case studies, but I'll just mention, obviously, probably the very, very famous anomaly detection case. And then we conclude. Right. So, yeah, these are like self-explanatory. We have a lot of data, and it's hard to find in the data what is anomalous, or so the statistical idea with respect to this is outliers, right? Now, depending on what you're doing, so I'm now talking about, in your real work situation after I realize that many of you are going for interviews and things, right? In your work situation, or in real life, right? When you have a data set, statisticians call this outlier detection. But the literature on outlier detection sometimes is quite different to the literature on anomaly detection. Literature on outlier detection is dominated by statistical techniques. Anomaly detection has been, I think, coined because we have non-statistical techniques also. Right? Now the thing with this, why it's significant is, though they occur very infrequently, when they occur, their consequences can be massive, dramatic, right? And often in a negative sense. So in statistics, we normally detect our outliers and just throw them away, right? This is a case when anomalies are important. So maybe to set the scene, I will tell you a real study when somebody from the medical faculty gave us some data of patients, elderly patients. All of them had some problems, either diabetes or heart conditions and so on. So they had a standard set of tests they did monthly. And this is like blood sugar, and pressure, and cholesterol levels, and things like that. So, and when they gave us the data set, they had all these readings, and they also had where the doctor has put a kind of an alert. Right? And when we looked at that data, we couldn't figure out what this alert was. Right? And so I will talk about that a little more when we look at the types of anomalies. Right? So what is an anomaly? Anomaly is a pattern in the data that does not conform to the expected behavior. Right? Humans are really, really good at this. Right? Sometimes these are called outliers, and in obviously in computing, as exceptions, peculiarities, surprise, etc. In normal English, it's like surprise. Yes, so the most common examples you may have heard is intrusion detection, cyber intrusion. So people come into your website or into your network and do stuff. And then, of course, the other common one is credit card fraud. So generally, there are some rules of thumb, and banks used to use that to detect these. So these are rule-based things, right? So suddenly, if you have very high purchases made on a credit card, or now people know that this is a way you detect, and so they would do not one high purchase, but several frequent smaller purchases. So all these patterns are now known. And of course, the people who do this also know that they are known, right? So they will always try some new patterns. And that's one of the key things about anomaly detection. It's not static, right? It keeps moving. Cyber intrusions are similar, right? So your web server, right, has some other kind of traffic. And so, okay, so in fact, a lot of it is rule-based, and we have on our VLE something called high-risk students. Right, high-risk students are students that are showing signs of dropping off a course. Right, so I get alerts. I may have got alerts about some of you. Right, but then the idea is, then we go and look, and we see that they have. You see that it's a rule-based thing, right? So they haven't accessed the VLE for a certain number of days consecutively, or they haven't submitted assignments or things like that. Right? So these are all rule-based things. So we are trying to see how we can do better. Right, so here's a simple example. We have like two variables. Should have been called x1, x2 instead of x and y, because x and y sounds like a response variable. Y sounds like a response variable. But these are x1, x2. So two attributes, and when we plot the data points for these two attributes, we realize most of them are either n1 or n2, and these may, I don't know, these may fall into some known kinds of behavior patterns, right? But we see that there's O1 and O2 that are kind of outliers here, anomalies. And what is significant about anomalies, O3 may have had an anomaly, but then more are starting to join. So let's say, I don't know, let's say this is a completely artificial synthetic example, but there were two types of behaviors on our VLE, let's say, N1 type and N2 type. I won't say what these are, but and then these two are falling outside that, and then O3 was first a single person, and then more started joining. So maybe this behavior started coming after the lockdown, right? So then it kind of ceases to become an anomaly. It's a third type. It is still an anomaly. So points in the region O3 are, all the points are kind of anomalies. And then you have to, of course, you have to find the reason. So generally, these anomalies probably pertain to, I don't know, somebody illness or something happened. Whereas this anomaly, same person, I mean, lots of people can't fall ill at the same time and so on. So this becomes interesting, and then maybe this pertains to the fact that people's behavior changed owing to the lockdown. And they are similar in some way. Okay, so this is very, very kind of an abstract example, but and these there are related problems to anomaly detection, rare class mining. So that example I just put is probably a rare class. Chance discovery. I think this comes from some other discipline. Novelty detection, right? So we want to, the reason why outliers, in the statistical concept of outliers is where we kind of have to remove them, right? But obviously in something like novelty detection, you don't want to remove them. Those are the ones you are trying to detect, right? Those are the interesting points, right? And then you try to see why. Exception mining. So you may find literature using these different phrases. Noise removal is probably the more common thing with communications and audio, video processing, and also of course statistics. Black Swan is a very famous book, right? The Impact of the Highly Improbable by this Nassim Taleb. Why he called this Black Swan, I think I have explained this before, but swans, as we all know and we are taught in school, are white, right? So swans are white. And only in the 20th century did someone actually go to some part of Australia, I believe, and they saw something swimming in the water, a black bird, black duck-like. So obviously they have ways of capturing or tranquilizing or whatever, and then studying them. And they studied and they found that lots of similarities with the swan, and there are biological phenotype. It's called phenotype. That is characteristics that are visible that were used to finally conclude that this was in fact a swan, right? Later on, of course, DNA analysis and also showed that it's a swan. And so millions of white swans didn't prove that swans are white. And that's one of the things I usually start with in my research methods lectures, right? So you say, will the sun rise tomorrow? Cannot be proved, right? Because it has done so for hundreds of billions of years or whatever, or well, I don't know, so many million years. That is not proof that it will, right? So, and this swan, black swan is an example of that, right? So before the black swan, people had seen hundreds of thousands of swans and they were all white. But that didn't prove that swans are white, and much later they found black swan. Right, so that's a philosophical book actually. Right. So what are the challenges? One of the challenges is how do you define normal? Right? How do you define normal? A representative normal. Color is not good. So that's one problem. Then the boundary, right? So let's say you think of normal, but what is the boundary? How far from this normal is an anomaly? Now, also be mindful that the diagram I showed you had only 2 attributes, right? If you have 3, you can still probably visualize. 4, 5, 6, it's going to be really, really hard just looking at the data to even figure out what is normal, right? So for instance, if I give, I don't know, your height and weight and I don't know, some other, so those are physical factors, and then some other things like your A-level Z-score and GPA, current GPA, there's another type of data. And then they give you your hometown. And so you give those different kinds of data. And then you try to find whether there's an anomaly. Right? And obviously, you can't do it visually. So you need to find ways of defining this normal and then find how far do you have to go to become an anomaly. Now, the exact concept of anomaly or outlier also is different for depending on the domain, right? So, and we have seen this in the clustering lecture. We said there are some algorithms that, for instance, work. Then the density-based algorithm, I didn't really explain that too much. The density-based algorithms where data points are situated very close to each other. And so a slight variation from that will automatically make it an anomaly. Right? But other types of data is where data is kind of spread out a bit. Then the anomaly is quite different. Now, of course, this is probably from the point of view of data analytics, the biggest problem is the availability of labeled data, and particularly labeled data of the anomalous type, right? If you want to do a typical supervised classification task, you have to have enough examples of the normal and the anomaly. And that's often quite hard, right? So let's say you want to detect credit card fraud, right? If you collect data for a year, millions of records, all normal, right? And then there may be a few anomalies, right? So a massively unbalanced data set. In addition, of course, data might contain noise, genuine noise. Right? And this last one, normal behavior can keep evolving. That's so the example I gave with the BLE identifying students at risk may be a good example. So when the lockdown came, the behavior changed. So the normal behavior also can change. Right. So these are some aspects of this problem, right? We need to worry about the nature of the input data because of that, right? Because the outlier will be dependent on the nature of the input data. Availability of supervision. Do we have data that is labeled, enough data of the anomalous class that is labeled? Now, one of the, okay, we will come to that later. Type of anomaly, we will look at this. There are 3 types commonly identified, and in your task 4, you will have a description of this. Right? They may use, first 2 are common, the third one often may not be called structural, but I mean, the idea is the same. And then what do we expect as output? Then how do we evaluate? Right. So here's the most common type of data is these what are called tabular data or record data, right? I think last time I may have discussed, when you say tabular data, what you normally mean is that each column can have a different data type. of course, each row in that column has to have the same data type. So here there's an IP address and time and port and a number of bytes and so on, right? And of course, the simple case is univariate data, but we normally have multivariate data, right? So this, as opposed to, let's say, if you are dealing in images or text or even audio, what tends to happen is we convert them into vectors, right? Now this is for the first data point. This is the vector, and this vector is heterogeneous, right? Different data types. If you are dealing with images, video, audio, text, and so on, then when we have to vectorize them, find embeddings for them, and those are then homogeneous because for each data point you will have a vector of numbers usually, right? And so the task 5 on text analytics is an example, and of course if you have done any image classification, then you would have come to the same kind of feature extraction method, right? You extract vectors, numeric vectors. Okay, so this shows what I just mentioned. The data types themselves can be complex, sequential, right? So this our DNA is sequential, and the temporal data is also sequential, like so the stock market share prices, something is also sequential. Then spatial, okay, there can be so most image, video things are spatial. And that's why in deep learning, the techniques used for these kind of things, the different techniques used for these kind of things, right? So RNN-based things are used for sequential things, and CNN-based things are used for spatial. And of course, combinations of these are used for both types. And then you may have spatio-temporal, right? So this world map is supposed to show that, right? It is spatial as well as changes according to the season. Sorry, there's a small occlusion here. Graph. There can be like a graph-based structure. So this is more or less like a ontology, right, of in shipping, and so you may have different relationships between the data. So each of these links has a different label. Right? So you may have complex data like that. Right. So the big question for anomaly detection is whether there is labeled data or not. And of course, if there is labeled data, we know that we will prefer to do supervised. Right? So this has to have labels for both normal and anomalies, right? And so this is what is usually called rare class mining, right? And so you may say, right, what is the difference between this and normal supervised learning? We will, I think, in the next slide, look at that. Semi-supervised anomaly detection is, this is where we have labels only for the normal data. Right? Actually, the word semi-supervised doesn't only refer to this type of case. You may have semi-supervised cases where only a few data are labeled, right? In other, not in anomaly detection, in other, let's say, in a typical classification task, you have 1,000 data points, but you have only 100 labeled, right? So then that can be also called semi-supervised. Right? Here, semi-supervised means only the normal data is labeled. I mean, you have labeled only for normal data. and there's another thing here is that anomalies, right? So why it's different from normal supervised or semi-supervised learning is because anomalies may not be easy to characterize, right? So normal data points can be characterized because they kind of form into a group or a cluster. But anomalies may not fall into a cluster, like in that case of, the third point became a little cluster, right? But anomalies can happen everywhere. So therefore, that's another reason why it's a bit hard to do supervised learning for anomalies, because each anomaly can be quite different from the other anomalies. And then, of course, we have unsupervised anomaly detection, which is probably the more common type, right? Because we don't have labels, right? And this is based on the assumption that anomalies are very rare compared to the normal data. So, and of course, we have already seen in clustering, right? We use distance as a metric to detect membership in a cluster. Right. So these three types of anomalies, yes. So the collective anomalies is more common than structural anomalies, but the idea is the same. Right. I think in the task 4 kind of worksheet you have, it is called collective anomalies. So point anomalies. Let me just go back to that example I gave you, the real example I gave you. So we had a small, those days we used to have kind of slightly different way of doing group projects and things like that. No, but this was an individual project. This was an individual project of someone, but I forget whether it was, I think that we used to also have like independent study and things like that. So this was a small task, given this task of, I don't know, 60 patients or whatever. Each person's sugar, cholesterol, all these things are given. And then one doctor, the specialist, had marked some places for those patients as alerts. Now, when he looked at the data, if you looked at, let's say, their blood sugar, there was no sudden rise in that place. In fact, in some cases, there was no sudden rise or dip in any of those readings, cholesterol, blood sugar, pressure. All of them were, I mean, they were abnormal, like, because these are all patients, they were abnormally high, either the cholesterol or the blood sugar, or sometimes more than one thing were high most of the time, right? So that's an example of this third type. All those taken together only formed an anomaly. Individually, all the readings appear to be okay. So let's look at the easiest type of an anomaly to identify as is point anomalies, right? So these are point anomalies. And that's the most easy, not to identify, but to characterize, that's the easiest. Contextual anomalies is where, these are not anomalies, but this may be an anomaly, right? Because we expect this seasonal effect to go straight like this. Now this one, though it has come down here, it's normal. We expect that to happen around January, right? So in this context, having this low value is an anomaly. Now, this is a fairly obvious anomaly because it has affected a short period. But let's say, what if you had this thing like this, and then here, sorry. Let's say here, sorry. What's happening? Right, if you had this, then I mean that would also be an anomaly in the context. That means in this season this should be higher. And obviously, this would have happened to our tourist arrivals in 2020 and 2021, right? So these will also be anomalies. I mean, like 10 years from now, when people use data sets, right? They will have forgotten all about this, but they will be able to detect. Okay, there are 2 years where this is like really flat. Collective analysis, anomalies, collection of related data instances is anomalous. And so here it requires relationship among data. And of course, these examples are all showing single data, right? So single attribute, right? So obviously these are not a very, that's why I said this is not such a good example, right? The example I gave you about medical data is probably better. So there are several readings, and if you plot each one like this, you won't find an anomaly, right? But when all 3-4 readings come together, right, the specialist has realized, okay, I don't know, maybe if the pressure has gone up, but the blood sugar has gone down or the cholesterol has gone down, then together those things cause an alert, right? And so collective anomalies are things where only in the combination that they are anomalies. Otherwise, individually, the attributes don't have any anomalies. Now, it turned out that a little backstory on that is that, so we gave this data set and one student did some work on it, and the student was not very happy, we were also not very happy, and but managed to say give some general characteristics of the data. The next year, so because this was a problem, the next year, I don't know whether that student identified at the end or whether we kind of read enough literature by then. The main difference was that in the first student's work, all the literature was related to outlier detection. Right? So most were statistical techniques, and they pertain to point-wise anomalies, point anomalies. And so the second student, by that time, we also had figured this out, and we said there's a near synonym for detection. There was a much more diverse set of literature, right, and a diverse set of techniques. And so that's an example I give people when you're doing research methods to show that your search terms sometimes can be significant or even critical. Right. So the output of the anomaly detection, there are two things. One is, of course, a label, right? So we label it as an anomaly. Or another way is to give a score, right? So which means it's not yes, no, not a binary decision, but a score which gives the anomaliness, right? The score of anomaliness of a data point. And then in those cases, we have to figure out some threshold and say beyond that threshold is an anomaly. Okay, so why usual classification techniques are hard to use is in typical, say, intrusion detection, where we have network traffic is 99.9% normal data and only 0.1% intrusions. So if we create a classifier that learns to tag everything as normal, right, we have 99.9% accuracy, right? So accuracy is not a very good measure, right, for evaluating anomaly. So instead, we use recall is one important thing. So the ratio between the number of correctly detected anomalies and the total number of anomalies, we want to detect that. Right? Then false positive rate. This is also very important. So we may get everything that is actual anomaly, our thing detects as anomaly, good, but we have a high false positive rate. That means a lot of normal things are also recorded as anomalies. Of course, it will affect the accuracy as well. And then, of course, we know the ROC curve, and we can figure out the area under that curve, right? Obviously, the ideal, which doesn't happen, is if the curve goes along this y-axis and then along the top, right? So, the worst is if the thing is straight across the middle, right? I assume these things you have done, but this is supposed to be a straight line. If it goes below this, right, you can always invert, right? So you say, when it says positive, I take the negative. When it says negative, I take positive. So going below that line doesn't mean anything, right? But the straight line is the worst. That means it's like saying positive, negative randomly. So anything above that straight line is good, but the further it is, the better. So this red line is better than this black line or blue line or whatever. But this green one is even better. Okay, so what are the applications? We have already seen network intrusion. I mean, this is one of the most common things. Credit card fraud detection, but there are many others. Right? In health care, I mean, you can imagine. So recently, we had this case of someone. Government jobs require you to, take your medical, right? That means, I don't know, even some private jobs may require you to do the medical. And so this person went and did the medical, and with some other friends and so on, and they all did it together, and this person was stopped. So she was wondering what had happened. They didn't say, right? Said to come the next day. To cut a long story short, what had happened is they, in the X-ray, they detected some anomaly, right, near the lungs. Now, these days, so these are not doctors; these are just, radiologists and things. So they have got so tuned to detecting COVID in your lungs, right? With the just looking at the X-ray, they were able to detect it, and then, of course, the person didn't realize that she had COVID. Right? It had been just like a cough or a cold or something. But so obviously that kind of thing is really about detecting anomalies, right? Because everybody's lung doesn't look the same, right? The X-rays don't look the same. Industrial damage detection, right, is really, really crucial. I think you may have heard of the Apollo 13, I believe. You know, everything is double checked, triple checked, 100 times checked, and yet when it hit the upper atmosphere, it kind of burst and split into a million pieces. So, can you detect those things? Image processing, video surveillance, right? The old method is, of course, to have a security guard, right, with this single screen, which has about 20 little screens, something like what we do when we have video on in Zoom, right? So this security man is supposed to look at all these 20 or 30 things and detect anomalies. I mean, actually, it's quite laborious, but and prone to fatigue and so on. So how do you do that using image processing? And then novelty detection in text mining. So these are all applications. I'm really not going to talk about these individually, right? As I said, I'm still quite focused to keep this thing within 90 minutes, right? So this is for background information for you to go through, and if you and also probably this is fleshed out in the exercise task 4 for you in text form. So I'm not really, I mean, the examples will be a bit different and so on. Industrial damage, aircraft engines and so on, right? How do you detect, I mean, not just visually, right? Thermal, right? Temperature, vibration, right? In that, I think in the Apollo 13, it was something to do with vibration caused at low temperatures, high temperatures, I think. Right? So they hadn't, it was not tested at the particular temperature that it would reach. Image processing. So yeah, so this is, I forget what this image is, but you can imagine. These are used for military things, for surveillance and things like that, of landscapes, as well as, body organs and things like that. Mammography, right, for breast cancer. And you may increasingly find, as I found somewhere in some airport, suddenly guys came and kind of took a guy who was standing about 5 feet away from me. And he, I mean, I didn't think anything of the person, but obviously they had, and that could have been manual, of course, that could have been manual, that they kind of followed the person for a while. And, if a person is looking around and, behaving in a suspicious way, humans are very good at detecting that, except that you will have to have, in a place like an airport where there are thousands and thousands of people, can imagine the number of eyeballs needed to detect, anomaly. I don't know whether they were using a system, anomaly detection system, so that may alert them, and then they start monitoring the person, and then so they just, I mean, the person didn't know also why it was being taken in. And I didn't know, obviously, because of course I wasn't observing the person, but it was just another passenger next to me, right? I mean, in the airport. Right. So this is kind of aiming to be a taxonomy for anomaly detection techniques, right? And by far the common type of anomaly we try to detect is point anomaly detection. And that's why the next few slides will talk about classification-based techniques. By the way, rule-based is also a classification-based thing. Neural networks, SVM. There can be so many. We know the naive-based. We can name a lot of the algorithms. Here, neighbor-based ones. Okay, so nearest neighbor is another classification method, but this is kind of singled out here because you can do it either density-based or distance-based. The common one is distance-based, but there are some cases where density-based is needed. Clustering, yeah. So again, that means these two are related, right? Because you don't have the only difference could be that in the nearest neighbor-based, you do have what is called a training set, right? A set of prior data, whereas in clustering we don't have. In statistical, so these are the things that people typically use for outlier detection. And then there are others, information theory based, and visualization. Of course, visualization is another way, right? We have highly developed visual system, and so that is another way. Now, apart from point anomaly detection, I said that these two are commonly identified in the literature, like contextual anomaly, and that means in that context, so that value is not anomalous, but in that context, it is anomalous. And collective anomalies is where, just one reading, one attribute is not anomalous, but the totality of the collective, the attributes is anomalous. Now, these two are like things that have happened more recently. And in fact, it is more about, not about a type, but about a way of doing. Online anomaly detection is where, as I said earlier, you have this thing that normal behavior also evolves. Right? So if normal behavior evolves, you need to keep changing your model. Right? So online stands for that. It doesn't mean, online as in, the normal meaning we say for online shopping. Or it is more about accounting for the changing nature of data and distributed anomaly detection. Right? Sometimes anomaly is not in one place. So we are going to look at point anomaly, and in that classification base. Again, this is for completeness, these slides, but I'm not going to go through these. You can have a look at this. The big problem here is class imbalance, right? Class imbalance. So how do you get enough data of the anomalous class? If you have, then of course you can use those. Right? What normally happens is that we manipulate the data by oversampling, undersampling, or generating artificial examples, normally called synthetic examples. And these are some methods, right? Probably SMART is a common technique, and there are libraries that do this automatically. I'm not quite sure whether RapidMiner has that. These are some examples of, so obviously you can oversample the REA class, right? Sampling means, right, usually, so we have, let's say, 2 classes, you can have any number of classes, and you can sample with replacement. So let's say we have 10,000 normal records and 100 anomalies. What we do is we sample with replacement from this 100 class and bring it up to 10,000. Random sample. Now that may sound extreme. The other side, downsampling, undersampling is as extreme. That is, you take random, you only take 100 random samples. Randomly, you sample 100 out of the 10,000 class. So then you have 100 of both classes. Right? That is undersampling. Oversampling is where you sample with replacement 10,000 from the 100 class also. And you can see both have undersampling. Sorry, we are talking about oversampling. Oversampling obviously has the idea of overtraining on a limited set of types of anomalies. Right? There may be many other types of anomalies, but you are only overtraining on these 100 types because you are extending it to 10,000. Undersampling has the other problem. Okay, you're only taking 100 out of the 10,000. How can you take a representative sample of 100 from 10,000? Probably very, very hard. And you can do a combination of these. So you can say, right, I'm not going to do 10,000, I'm going to do 1,000. So I'm going to randomly sample 1,000 out of the 10,000. That's going to be more representative than getting just 100. And I'm going to oversample the 100 up to 1,000. That's not as bad as oversampling it to 10,000. So that combination. And then, of course, synthetic data, right? So getting synthetic data, right? SMOT is probably one of the most known types, but you can imagine there are various, this is very task dependent. So for in machine translation, for instance, we say we can generate synthetic samples by doing what is called back translation. Right? We translate back from a previous version of our translator and use those as new examples. Right? In vision, you may have seen you can do various algorithmic operations, right? Rotation, or blurring, or things like that, mirror imaging, and things like that to increase synthetic data. Right? So this is very dependent on the application, how you create these artificial or synthetic data. Right. So we use techniques from supervised algorithms. Right. Nearest neighbor. Yeah. So as I said, this is basically for your. Maybe we are running out of time, so you can go through these and just try to figure out. So you will be using this local outlier factor approach in your in the task 4, right, on anomaly detection. And there are 5 different things you will do. There are 5 exercises, as was with some of the other with the recommendation systems. Right. Cluster based. Okay, so we can use clustering, right? And again, you can have semi-supervised, but more commonly it is unsupervised. What are anomalies? Well, anomalies are those points that don't fit into any cluster, right? Or that fit into a small cluster. And you may find, in the example I gave, I think, in the zoo animals thing, I think, right? When you cluster, you may have found some clusters with 1 point or 2 points. Right? So those will be outliers. And typically in zoo animals, outliers are things like whales because they look like fish, but they are mammals, and ostrich because they look like birds and don't fly, and things like that. And then low density clusters where density matters, right? And some advantages, disadvantages, and so on. And then this, there's another algorithm called find out, but actually now in RapidMiner you will have some other things like this cluster-based. Like the earlier one, local outlier factor, there's a cluster-based local outlier factor. Sorry. And so you will use some of these in your lab sheet. Statistical, so these are the common techniques we use for outlier detection. So I'm going to skip these. There are also non-parametric methods, right? But the more common is parametric methods. So here's an example of statistical technique. This example, I think you can skip this statistical part, right? And you can also skip the others part, right? Information theory based techniques, just some references. But we are not really going to. Most of this is for your background information, right? So I'm not going to test you on these things. Visualization, as I said, this is where, so that example of, the airport person detecting anomalous behavior, you can imagine that, looking at videos is really, really hard. But if you can have a system that can detect and visualize, show a visualization where, red, green, yellow, and so on, rather than the actual videos, then basically you keep the human in the loop, and those alerts are then followed up, let's say in that case using real video. There's also some techniques, these techniques are a bit outdated now, so we don't need to look at that. Visual data mining, right? So this is about if you have a traffic system, or in this case it's a phone call pattern system, right? You can, these of course obviously normal people can't do, only the operators are able to do this, but you can imagine a traffic system that is able to visually, right, see some junctions becoming red, other junctions are becoming yellow, but green means it's flowing nicely and things like that. Right, so I've already discussed what contextual anomaly is, right? Techniques for doing this are very dependent on the application. So I'm not going to, there are no kind of algorithms, but we use algorithms that we use for pointwise in a different context. Things like conditional anomaly detection. Collective anomalies, and so these try to detect anomalies with respect to points close by to them, right? Whether they are either sequentially close by or spatially close by. And of course, there can be some that are graphically close by. A lot of these are used now in, for instance, in genomics and proteomics in bioinformatics. For climate data, which is very complex and intrusion, so high density data. is one particular technique, but I mean, obviously, I'm not expecting you to look at the know these. So online anomaly detection means things where situations where things you have streaming data, right? The data keeps coming in through video or through sensors, right? And of course, you can imagine something like Twitter, right, as a stream, right, or even Facebook, right? And then things like ATM or credit card, right? Those things come as streams and they keep changing. That's the main thing. How do you do? And this is related to what is called online machine learning, online learning. And you use similar techniques that we use for online learning, machine learning. Distributed is where the data is actually coming from multiple sources, right? And so there are particular considerations for that kind of situation. So these last two are actually not really types of anomaly, but to do with the nature of data. So I'm just skipping that. But so basically, anomaly are important mainly because the opposite of what we do in statistical outlier detection, which is to throw away the data, here it is the anomalous data that is of interest. Right? That's a critical difference between anomaly detection and, let's say, outlier detection. And there are applications in lots of areas. Yeah, so the exact nature, whether it's online or distributed or collective or contextual, depends on the domain, and so we need to have different approaches to formulate first and then solve the problem. Okay, right. So very quickly, let me take you to the course page, right? So this submission link was disabled, so I've enabled it, right? This is for actually should have been for last week, so now I'm setting it for this week's task. But in addition, I've set a little what do you call it? Descriptive to talk about the concept. This is just one A4 page, right? What do you understand by associative rule mining, market basket analysis, and recommender system? How are they related? How are they different, and the techniques and so on? So it's a kind of writing assignment. Right? This is the task, and you're supposed to do it by since it was supposed to be done last week, I have set it as 20 seconds. So this is something you should be able to do. And that's why I'm not setting the submission for task 4 or task 3. Task 3 or task 4, I'm not setting a submission because you can do it. I highly encourage you to do this. Task 3 was already there, right? I hope some of you at least have done that. Task 4, I'm not. I've given the task, and this is the slide set that I just finished. And I've also put task 5. This is mainly for you to help you with the assignment, right? The final assignment, which I haven't yet made visible, but I will just quickly give an idea of what it is. So I have said due date is 6th January, but I may put it back by a week, right? So basically organizations are eager to gather views of their main stakeholders, right? These are referred to as customers, right? Via online forums, right? So a common way to get a bird's eye view of this, right, without reading all the feedback they receive, right, is to kind of look at the sentiment. I mean, and that's a common task, sentiment analysis. Are people happy? Are people sad? Right? And, sorry, happy or unhappy? Now, some people actually give also suggestions. And those are really valuable. Right? So some are just saying this is, food here is terrible or something like that. Others say, well, if you could, do this, your room would look much more inviting or something like that. So we want to be able to typically hotel or organization would like to distinguish between suggestions and non-suggestions. And once you have suggestions, maybe the suggestions are about various aspects, how to improve your reception, how to improve your rooms, how to improve your services, how to improve your food, facilities, and so on. So you want to know which aspect it's about, right? So this thing is about that, right? So you're supposed to download the data here. Now this data is a suggestion mining data set, so it has suggestions from different domains. I'm asking you to download only the hotel reviews, right? And it will have hotel reviews training and hotel reviews testing. So we are not going to worry about training and testing. We are going to take all into a single merged. Sorry, I had to replace this, right? I gave this kind of assignment using Python. So I'm going to change this. That's why I haven't yet uploaded it. So basically, what you have to do is to take it into RapidMiner as a single data set. So that means the CSV files will have to join in some way, right? And then clean the data set. So one of the ways you clean is, of course, by removing stop words and taking on lemmatization. So for this, that text mining task 5 will give you a lot of help. Then I want you to know what is the number of posts that are suggestions and how many are non-suggestions. Right? So this you will have to do in some way using RapidMiner. And this is very important for you to figure out the dimensions of the data set. Right? So that gives you a dimension, okay, so many are suggestions, so many are non-suggestions. That's marked, right? That's a labeled data set. So you should be able to get that. And then I also want you to know what is the total number of words in this data set for all the suggestions and non-suggestions, and the number of unique words in the whole data set. This is important because it is the number of unique words that are used to for creating our models, bag of words and TF-IDF. These are the two models that I'm wanting you to do, right? So these are feature extraction methods. And then use any two. I've said two, but there are lots of algorithms in RapidMiner. Two relevant. So in your write-up, you have to say why you selected these particular algorithms to classify between suggestions and non-suggestions. And I want you to give the confusion matrices, all this in your report, right? So there'll be 4 confusion matrices. There's 2 feature extraction methods and 2 algorithms. So there should be 4 matrices for a held out or a test data set. And how you would define the training and test is up to you. I haven't said what percentage or so it's quite open-ended. And then I have said suggest any strategies you may use to improve the performance of this above classifier and see whether you can implement a better system than what you proposed in this. In other words, can you do better than the 4 confusion matrices you get here by doing something? When I say doing something, you can do it in the pre-processing, right? In these steps like cleaning, removing, stop words, lemmatizing, those things you may change. You may change the feature extraction instead of Pythagoras and TF, I don't know, n-grams or some embedding or whatever. And instead of these algorithms, I don't know, some other ensemble or something else. And then part D is in general, suggestions can be categorized into particular aspects of the service provided by the hotel. Propose an unsupervised approach to categorize suggestions. So here we are now going to remove all the non-suggestions, only take suggestions and see whether you can use an unsupervised way to kind of cluster them into different aspects of the service. And I'm asking how could the optimal set be determined? And so this is related to our clustering session we had last time, how we determine an ideal number of clusters. And then I say implement your, and well, not print, I'm not saying print, but describe, right, in your document. And do some visualization to show that this is reasonable. Right? All this in your report, right? And the last part of the report is discuss without implementing any issues with the data and models used, and any improvements that you would suggest to make the overall model more useful and perform better. Right? And here I expect a reflection on the whole course task. So for instance, you put yourself in the shoes of the hotel owner and you say, right, how could I do this better? It could be range from the kind of data you collect to the way you pre-process, I mean, maybe human in the loop systems, or, you know, it can be anything here. So it's very open-ended part E. And the submission is that you have to give these solutions from part A through E in a report in which you actually put screenshots of your workflows, right? And the description. Okay, so for each part, a descriptive summary with an interpretation. And you finally convert your report into a PDF and submit it together with all the workflow files as a single compressed file, where the file name is your index number.zip. Right? So I will also set up a forum for this. So if there are any clarifications you want to make, we will do in that forum. Right? So this will be up before the end of today. Right? Okay, so we are 90 minutes more or less up. Any questions, clarifications? And so this will end all the continuous assessment part for this course. Right? In January, we will actually look at how to use cloud services to do this. We will take slightly different use cases. But the idea is that, you know, if in real work situations, if you go out of all these data sets that you are working with are kind of, they are realistic, but they are small, right? So, and also we are stopping at finding the performance, right? So we will see one big difference when we go into a cloud-based system is that we have to think of the entire life cycle. Some people call this MLOps, like DevOps, MLOps, but we will touch on that, right? And but I will not give any assignments from that, right? Because I think all the assignments will start coming in January, right? And then I think in February we have the exams. I have forgotten, but something like that. Any questions, comments?
Excuse me, sir.
Yeah.
So when is this assignment due?
So currently I said 6th January, but I was going to make this 13th January so that we also meet after that. Like we will have a lecture after that.
Okay, sir. Thank you.
So this hasn't been uploaded because of these problems. So I'm changing this to 13th and changing this pandas and a few things in it and upload it by before end of the day. We have 3 sessions. Right? I think this is on, if I'm not mistaken, Fridays are 7th, 14th, 21st. 14th is an issue, right? It's what is it? Thai Pongal, right? So we may have to reschedule that one. Okay, so have a good day. Have a productive weekend also. And good luck with your projects.
Thank you, sir.